Hi, everyone, and welcome to today's ICP Zero to Dapp Educate workshop. We are going to invite our speaker, Yotam, to the stage, who will be talking to you guys today about HTTP calls, which was going to be really exciting. So pop any questions that you have throughout the session into the questions tab. And I'm sure he'll be happy to answer any questions that you have. In the meantime, hi, Yotam, how are you?
Hi, I'm good, thank you. Hi, Clara.
Good, nice to meet you. I hope I pronounced your name correctly.
Yes, yeah.
Good, good. So yeah, in the meantime, guys, while Yotam gets his slide ready and stuff, please remember to submit the weekly challenge for last week if you haven't already. There's still time to submit it, so no worries. And this week's challenge is going to be announced tomorrow, and I will send you all the information about that. So that's it for me for now, and enjoy the session, guys.
Thank you. So welcome, everyone. I'm happy to be here and talk today about the HTTPS Outcalls. I kind of assume that you know a little bit about the internet computer already, so we can delve into this topic and not spend too much time on introductions. But if there are any questions, feel free to ask me. I'm taking a look on the side on the questions tab. So if you want to ask anything, just pop it there and I'll find the time to answer. So let me start with what I'm going to talk about. I'm going to give a brief introduction what HTTPS outcalls are, because they're very different than if you developed on other blockchains before. It's something you probably haven't seen because it's very unique to the internet computer. Then I'll try to explain how this enables interactions with the outside world, with Web 2 specifically, how it replaces oracles in many cases. Then I'm going to dive a bit into the technical details on how it works, not too much. But if you have further questions after this presentation, you can, of course, ask me. And I will also explain the exchange rate canister, which is not directly related to HTTPS outcalls. It's a service on the internet computer. It's a canister, just like any other canister you could develop, that lets you get exchange rates. It's implemented using the HTTPS outcalls feature, and it's available for everyone to use instead of implement their own canister for getting exchange rates. And I have some links on how to learn more, and I guess you can have the slides later and use these links to go to the documentation and the developer docs and the sample dApps that we have implemented already with HTTPS outcalls. So with that, I will start. So you should, I hope, know that what canisters are already. These are pieces of software applications running on the internet computer. On other chains, they might be called smart contracts. We call them canisters or canister smart contracts. And I think you should also know the difference. The canisters can do much more than smart contracts on other networks usually. So the end user communicates with them with some user experience that they have. It might be a user interface or an application on the phone or anything like that. Depends on the canister. The developer deploys the canister to the internet computer and gets the communication from the users in the shape of requests to the canister, based on the front end, how the front end works. And a canister is deployed on a certain subnet of the internet computer, because the internet computer is sharded into multiple blockchains, if you want to call it, and the canister it lives on one specific subnet. And by the way, an application could live on multiple subnets by leveraging multiple canisters talking to each other. But one canister lives on one subnet, and the subnet is is composed of some servers that live in different data centers around the world. And that's how you get the decentralization of the internet computer, because every node on a single subnet would probably, with very high probability, be in a different data center and even in a different continent, or at least in a different country. So when you deploy a canister to the internet computer, you get a distributed application running on multiple nodes and all the benefits of that. I won't get into that too much, because that's not the topic of this talk, but it's important to understand that this canister, the code of this canister, is running on multiple nodes and in different places on the globe, and together they compose this subnet that executes the computation of that canister. So that was the important part I wanted to stress here. Now, when the canister makes a call or something, it actually being executed on each and every node on the subnet. For example, an update call that changes the state needs to be computed by every node. And then they agree on the state change, and that's how the blockchain makes progress. Now, what are these HTTPS outcalls that we're talking about? In this case, the user may trigger, for example, an update call to the canister, and this update call might need to go to some external web server on the web. It doesn't have to be on a blockchain. It doesn't have to be on the internet computer. It could be any web server, to fetch some information from that server or to update some information on that server. So on a regular cloud-based system, we would use some sort of a REST API or issue some HTTP call to that server. But on a blockchain, on any other blockchain, that's just not possible. And the reason is that it's quite complex to do that. And you will see soon the technical details, you understand why. But on the internet computer, we achieve this. And what you get as a developer, the experience you get is that your canister can call any HTTP API, HTTPS, because we require it to be secure, get the response, the HTTP response, into the canister in memory, and according to that, do whatever they want with this information that they got into the memory. It could be given to the user, it could be aggregated somehow, it doesn't matter. You get it in memory, in your code, and you do whatever you want. And I'll show some examples soon. So yeah, so here is the first example, very simple one. Let's say there is a Web2 service to fetch the weather for tomorrow in London, for example, or anywhere on Earth, just give the name of the city or so. And the way it works is you send a GET request with this URL, whatever the server name is, and then the path is a weather, a question mark, and then some request parameters, the city, could be a date, whatever. And you send this request. If you know how HTTP requests are built, the syntax is like the method, which is get here, then the URL inside the server without the server name. And then the protocol details, like HTTP/1.1 means we're using protocol HTTP version 1.1, but it could be another version as well. And then there is a response coming back in HTTP. The protocol says the response, the first line of the response is composed of this HTTP version, and then some status code. 200 is okay, you probably know. 404 is not found, and so on. So it looks something like that, the first line. Then there are headers sometimes, or almost all the times. I don't include them here in the example just to make it simple. And then there is a line break and the content of the response. And here the content is, in this example, is a piece of JSON. So it says the condition would be sunny, the high temperature would be 20 degrees, the low temperature would be 10 degrees, and the unit is a centigrade, for example. You get this into the canister, and then you know that the weather in London tomorrow, let's say, would be this. And you can do something with it. I don't know, show it to the users, compute something based on that, whatever you want. Another option to use outcalls is to push data out to the network, for example, push notifications. So imagine that you have a web server for sending text messages, SMS messages, and you could send post requests to the server with this API that we see here. You send it to the URL /SMS, and then you have some headers maybe or something, and then in the content you have in some encoding, you have a destination number and the content that you want to send in this message. That's also possible. There is, as written here with star, a little caveat here, but I will touch it very soon. Of course, you could get prices of things like cryptocurrencies or commodities or whatever you want if you have the right API. And there are APIs for that. I will talk about them later as well. For example, from crypto exchanges, you can get the prices for, I don't know, any pair you want, ICP, USD, or whatever, for any specific time. And they will give you the time or the value for this time. So I don't know, let's say this is the ICP value or something like that. So you can get anything based on from these kind of APIs. I will talk about these kind of APIs soon again, because I think it's interesting for many DeFi applications. I see a question on the chat. Why can normal Ethereum smart contract call HTTPS? Yeah, it's kind of the way it's built. Maybe I'll get to that later after I explain the technical details, because I think it would be a bit clearer then. It has to do with the architecture of the internet computer and the way it works, and also the way we enable complex computation to be executed quite cheaply on Ethereum. Even if you could do that, assuming you overcome other difficulties, it would probably cost a really huge fortune to make one call. And the internet computer, it's cheaper to execute these operations. But I'll get to that. I'll try to remember this question, and if not, please remind me. There are many more APIs out there. You probably know many of them that you might want to use. I just give some examples. You could use, I don't know, Stripe for credit card charging or any other thing like that. Get flight status, prices for flights, or whatever, hotel booking, stocks, commodities, trading, and it's really open-ended because the amount of public APIs available there are like endless. So yeah, just use your imagination and then start thinking about APIs your Canister could connect to, and yeah, start building. So there is another question I see on latency. If we can simply call any API HTTP API endpoint, how is latency handled? Is a smart contract hosted on ICP depend on the data? So the contract is awaiting the call, and the call may take a few seconds or more than a few seconds. It depends on the web server as well, and on the inside of the internet computer, it has some latencies as well. But we're talking about a few seconds max, because the HTTP call itself would time out at some point. And it's async operation, so you could await on it, or you could use the future. We can discuss the SDK later, but there is a latency inherent here, but the smart contract can handle it with the way it wants with asynchronous coding. And does it support WebSockets? No, it doesn't. It's only for HTTP request and response. For WebSockets, there is a community project that allows for having WebSockets somehow. It's not very trivial because, well, I won't get into that now. It's a bit complex, but no, it does not support WebSockets. It's for a request and response, a single one every time. someone may ask, how is it different than the Oracle's model? So for those who doesn't know the Oracle's model, I will quickly explain. So in the Oracle model, the same canister you would have wanted to build would have needed to contact another smart contract or canister in our case that was deployed in the network by the Oracle or the Oracle provider or whoever operates it. And using a canister to canister call, this canister that this developer canister would have told the other one, look, I need this information. And this other canister, the Oracle's canister, would store this somewhere in its state. And so it cannot make a direct HTTPS call like we saw before. So instead, sorry, there is a problem with the animation here, but this screen now is good. The Oracle's infrastructure at some point, like an external server owned by the Oracle's provider or something like that, would call the Oracle smart contract here and find out that there is a pending request from another canister here. Then it will make the call to the web server, and then it will update the result in this smart contract. And then the result would be pushed to the other canister back. So if we look at the timeline, how it works, it looks something like that. Your canister or smart contract, whatever you want to call it, makes an inter-canister call to the Oracle smart contract. At some point, the Oracle's infrastructure polls this smart contract here and gets a response that there is an outstanding request. Then it makes the request to the corresponding web server, gets a response, it updates, it makes an update transaction to the smart contract of the Oracle, which then calls an inter-canister call to update the state of the original caller, the canister that initiated this. In HTTPS Outcalls, it's simpler because the canister directly calls the HTTP server. There is some complexity involved here, but not as nearly as complex as what you see on the left side. And it gets the response. I'll get to the complexity soon. It's not as simple as just HTTP request response and nothing else, but it's not much more than that. So now a bit how it works. So let's say we have this weather API because it's very simple and very easy to explain things with. And the canister wants to send this GET request that you see on the screen. The canister makes the call through the API of the internet computer, and the ICP protocol then executes this call by sending it through the different nodes. So each node, what it does, it issues the same request to the remote server. So the server does not get one request, it gets actually like 13 or whatever number of nodes there are on the corresponding subnet where the canister runs. Then the server responds to each one of them. And let's say it responded with this response. And then they aggregate it and agree on the response because we don't trust each server separately, each node separately. We need them to agree. We need 2/3 of them to agree on the content. Otherwise, the canister will get an error. But if they agree on the content, 2/3 of them at least, they go through consensus, the consensus protocol of the internet computer. Then the canister will receive this response. But that's a bit tricky because, I mean, if we have all the responses exactly the same as we see here in this picture because everyone behaves correctly and there is no other problem, then it's easy to reach consensus because the nodes will report the same content and they will agree on it, no problem. But let's say we have a malicious node in the network, because that could be, it's a blockchain. And this malicious node says it's going to be a snowstorm instead of partly cloudy. We don't want the canister to think there will be a snowstorm. But here, because if in this example we have 4 nodes, 2/3 of the node agree, so it's still easy to reach consensus. They will just ignore this other node, to the very least. They can do more. But let's say the problem is different. It's not malicious activity, but the response from the server is not as simple as we saw before, just a piece of text. It's a JSON object with a timestamp field of, let's say, the time where the response was created. And it could vary a few milliseconds from each other because the server responded 4 times. So now we have a problem. We cannot agree on the response. The response is completely different in every one of them. So what is an agreed upon result here? So how we do that is we're going to help the responses to be identical, or the developer should help the responses to be identical, the developer of the canister. And the way it does it is using a function that it supplies together with the request itself. So together with the request that we saw before, let's say it's the string that you see here, the developer of the canister also supplies a function that gets an HTTP response and returns an HTTP response, but on the way, it's supposed to transform this response somehow so that the responses are identical. So the developer knows what API it's using. The developer knows what the response structure and the syntax is. So it could do something like this very simplified transform function. It doesn't look like that in practice, but something like parse the JSON of the body of the response and then get the value of the field named result, and only return that as the response. And if that's the case, what happens now is when the nodes receive the different responses, each one of them will apply this transform function on the response that it got, and it will only report to the consensus protocol the result of this transform function. So what will happen then is that we will reach consensus over the transformed content, but not over the raw content that each node got separately. So if we take the example before and apply the transform function on each one of the responses, you can see that all the nodes will now get identical response, identical content to agree on. And then it's easy, again, to reach consensus. So before I go further, I see that there is one question and many messages in the chat, which I need to check as well. Consensus on a single data source, or you can issue a single HTTPS Outcall that use different APIs in order to validate data source. No, it would be consensus on the same data source. So the consensus is just that you sent a request from the canister and that you received the content that you're supposed to receive from this data source, that no node modified anything in the response, for example. But it's not a consensus on different data source for the same request. Let's say you have multiple data sources, you can check for the same request. Let's say you have, I don't know, Ethereum RPC server, and you could query the same information from different RPC endpoints, and verify that the RPC endpoints behave correctly. But that's not what we're talking about here. That's another layer above. Here, I'm talking about the making sure that the ICP protocol provides you with the correct response for the URL you requested on the specific server you requested. And that's it. Above that, the next layer, it's something to do in your application if you want to contact multiple servers and make sure they don't lie to you or something like that. What happens when the remote server has the concurrency of 1 request per second? If you get rate limited, it's a problem. If the remote server is heavily rate limiting, it's really a problem. You either wait, or if you get rate limited and you get I don't know, 429 error, then it would not work. You need to use a web server that allows more than a few requests per second. Do you need the entire HTTP response, content length, and so on, or can you build your outcall to drop connection at X amount of bytes. There is a mechanism to limit the number of bytes you receive from the network. It's actually part of the pricing as well. So there is an incentive to have requests that return small responses, because it costs more to operate the blockchain with bigger responses. The connection will be dropped. Do you need the entire response? Yes, we don't. There is no mechanism to say to the web server, don't send me these headers, right? So you will get the entire response. You can use the transform function to get rid of the headers, for example, if you don't need them, or to get rid of some content if you don't need it. That's what the transform function is for. How would this transform function work with prices? It depends. So I can talk about it a bit later when I talk about the exchange rate canister. If you get the real-time price, it's a problem, because you might get different prices, so it wouldn't work. But most APIs don't give you real-time prices anyway. They would give you prices for a specific timestamp. And you can ask, for example, 10 seconds in the past or 1 minute in the past. And then it should be fine, because for the specific timestamp, you should get the same price. Okay, I see there are many questions on the chat. I will follow only the questions on the questions tab. So if you have more, please ask there. Yeah, so let me continue, and then we can continue with questions soon. Some caveats that we have here. The first one is with post. It's quite a big one, because when you send 4 or 13 GET requests to the same server, that's kind of fine if the server answers you. As you said, it might be rate limiting very heavily, but in practice, we don't see that too much. Servers are supposed to respond to more than one request per second, so it's fine. It's more in the order of at least thousands or more. But if you send multiple post requests change the state on the remote server. GET requests shouldn't change the state, but post do. And if that's the case, and let's say we charge a credit card and we send a request to charge $100 from a credit card number. In this case, if we just do it, we will charge them, I don't know, 4 times in this example, or 13 times if we're talking about a standard IC subnet. So that's kind of a problem, right? You all agree, I guess. So the solution for that is to use APIs that support idempotency. There is a sort of like quasi-standard for idempotency key header that you provide this header with some string, and the API, if it supports it, what it would do is it will only execute the first one, and for the rest it will just return some response that it has been executed already or something like that. Then what you can do is, if you use this, you send this 4 or 13 times, or whatever number the size of the subnet is, and the card will only be charged once. It's your responsibility as the Canister developer to generate a new idempotency key with every new request. Next caveat for this feature is that it only supports IPv6. So what it means, the server, the remote server that you want to access, must have an IPv6 DNS record, this quadruple A record. So if it only has an A record, which is IPv4 entry, this would not work. And the reason for that is that the Internet Computer nodes only use IPv6. They don't use IPv4. And for now, there is no way around it. We have multiple ideas. None of them is really good. So we stick to that for now. And I know it limits the number of APIs, but we already see growing numbers since we launched this feature, and I hope they will grow further. Next caveat, it must be HTTPS. We enforce TLS, and we enforce the validity of the certificates. We use the default Linux root CI list, and the nodes will enforce this. Every node uses its own Linux tab to make the request, and it will enforce TLS and HTTPS on the connection. So the URLs must be HTTPS, and the connection, the certificate must be valid, and so on. Yeah, before I go further, I see a new question. Is there a % of required nodes to also get responses from HTTPS? I mean, 10 nodes make a call, only 5 get response, 4 have the same response, or it consensus. No, it needs to be 2/3 of the subnet. If the subnet is 13 nodes, for example, it means up to 4 or so can return or not return a response at all, or return a different response or something. But there must be 9 out of them that have the exact same response. Like string comparison, it would be the same. Or we actually hash them and we check that the hash is the same. So if a node doesn't get a response at all, it's a timeout. It's also sort of a response, and it's taken into account just as any other response. For cost, let's talk about the cost, because that's very important. It's not a cheap feature. There are multiple reasons for that. First of all, it's quite costly in terms of resources on the subnet. And second, we want to prevent denial of service attacks using this feature. So the feature is not super cheap, but it's not very expensive as well, especially if you compare it to oracles. So the costs are based on the subnet size, because the larger the subnet, the higher the cost is, because more nodes need to do the work. The size of the request and the size of the response. Now, the size of the request, it's not really the size of the request. The size of the response. It's not really the size of the response, like the size of response, but there is a parameter that you set to limit the size of the response, and you will use this parameter, the argument you give there, to calculate the cost. So you and the Internet Computer Platform know in advance, before making the call, how much it will cost, regardless of the actual size of the response. But I'll get to that soon. Just to explain the formula in a bit simplified way. This is for 30-node subnet, which is the standard application subnet on the Internet Computer. It will cost this number of cycles. Now, cycles are they might be confusing, so I made this graph here with cost with dollar cents, at least approximate, or SDR cents, maybe more correct, but it's almost the same. So a request, an empty request with no, like empty request and empty response, I mean, it's useless, but just as a baseline, would cost these numbers. On a certain 30-node subnet, it will cost 0.04 cents. And here on a 34-node subnet, it would cost 0.17 cents. But if you increase the size, for example, 1 kilobyte request, 1 kilobyte response, which is already useful sizes, you see it's not much more expensive than that, right? If you increase the size significantly, for example, the response is 1 megabyte, then you're going to pay a bit more, because this response is going to consume bandwidth. It's going to get into the block, the blockchain block, so it has its costs. And it's similar to the cost of ingress messages, by the way, because they kind of impose the same resource requirements. So on a 30-node subnet, such a request would be 10 cents. And on a 34-node subnet, it would go to 27 cents already, which is still not that expensive, but not cheap. I agree, but that's what it is. Now, another feature that we have from the Internet Computer and might be very useful for some of you, maybe, is a threshold DCDSA. So with threshold DCDSA, nodes can collectively sign anything with ECDSA curves. And that means they can, for example, if the remote server wants to verify the request, the signature, they can create a request with a signature included in it that was signed using this threshold DCDSA protocol. And the idea threshold DCDSA is that no node has the private key for the signature, but together the entire subnet that signs the threshold DCDSA signature has the keys as shares. If you know threshold signature, how they work, each node has a share. Together they generate the signature. None of them have the private key on its own. And then you send sign requests, and the server can verify this, and it's very powerful for the security of the application. Okay, before sample code, I see another question. Does this mean I could use a front-end Canister and HTTP Outcall, so say call an Infura API to get data from Ethereum or any chain with RPC, actually, which is all of them? Yes, and actually there is an effort on doing that as well, specifically on Ethereum and related chains and layer ones and so on, layer twos and so on. So yes, that's definitely possible. There are issues, but it's possible, and people are doing this, including within DFINITY, but also teams outside. Yeah. Okay, so here I have two examples. One with Motoko, which is a bit more involved. It's the first one, and another with Rust, which is super simple. And I include here in this QR code a link to more samples that we have on how to use this feature, just like we have for many other features. But let's try to go over here. I hope the font is not too small for you. But let's see. So we create a URL string, like whatever we want here. It's a bit involved because it calls the API for Coinbase Pro, and it gets the candles values. It's like the candles you see on the graphs for ICP to USD from a certain timestamp to a certain timestamp. And with 1 minute granularity. So it will create this candle with 1 minute granularity between these timestamps. Here in this example, it's the same. So we get one, but you could get more than one if you wanted to. Then we create the headers. So we need the host header and the user agent. And we create a transform context. Now, what is this transform context? I explained before, right? What the transform function does, it sanitizes the response so we can reach an agreement. So we have some transform function. This example, the entire example is available in this QR code, but so I don't include it here because it's a bit long. We actually need to do some work here to sanitize the responses from Coinbase. So this function does it. Here we just refer to it in Motoko by saying the function is transform. And the context, you could provide the transform function with a context because, as you see here, this function is kind of stateless. It just gets the raw response, but it doesn't know anything about why or when this call was made and what the purpose was. In some cases, we need this context to actually sanitize the response correctly. So we need some more information on how to, like, what is something about the context, like for example, for what date we requested the information, for what timestamp or so. So you could provide here.
Yotam, do you mind zooming in just a little bit? I think people are struggling to see what's on the screen. If possible.
How I can zoom in. I'm not sure.
You could probably just do like a Command+ to zoom in.
Yeah, let me. For some reason, it's no, it doesn't. Let me. I can try here maybe, and then.
If it doesn't work, then maybe you guys who are struggling to see stuff, you can like zoom in on your own screen, and that should probably help.
Maybe this is better now. I think it's a bit bigger.
Yeah, I think that works.
Okay, so this context here is empty, but it could be anything. It's just a blob, and you could use it in the transform function if you wanted to, there is an example for that, but I'm not getting into that too much now. Then we build the request itself. So there is some type that we need to fill in. It's like a struct with the URL, max response bytes. This is the limit for the maximal size of the response that I was talking about before, that is being used for charging and for actual limiting the response. So we will not read more than this number from the response socket when it comes back. And if it's bigger than that, if the response is bigger than that, the actual response, you will get an error. You will not get the first 1024 bytes, you will get an error. So you must know what is the maximal size you should expect from this call. It could be bigger than that, than the actual size, but it couldn't be smaller. You will get charged based on this value here and not based on the actual size. Then the headers, we built them before, above. Then a body, it could be supplied, but it's optional because this is a GET request, we don't need one. Then the method here in Motoko, we use this enum notation this way. And for transform, we provide this context that we built before. So now we have the request ready, but we haven't executed it yet because one thing we're missing is to pay for it. So in this case, the price is going to be something like that. Someone computed it, I don't know, I haven't checked it. But we add some cycles to the call, and then we make the call. We make the call using this ic.htp request function, and we pass as parameter the HTTP request struct that we built here, okay? Then we await on it here until we get a response. So the response is this type, HTTP response payload, and we call it HTTP response. And then we can decode it. That's just, I think, less interesting. I see some questions, so I'll try to answer, maybe because maybe they're related. There are many. Calling for API to get data from Ethereum kind of storage proof. I'm not sure I understand this question, I'm sorry. Since this is a bit low level, do you recommend to use Motoko or Rust CDK? That's really your choice. Both are capable of doing exactly the same thing, I think. I'm not a Motoko developer, I must say. I'm more used to Rust, but that's my personal opinion here. I think in Motoko, many things are much, much simpler when developing on the IC, so don't take my word on that. There are examples for both. Look at the examples and decide for yourself, especially if you're not Rust enthusiast. Is there any testnet where we can test this? Not sure how HTTP would fit into the testnet. Yeah, so actually you can test it with DFX locally on your computer. You can use DFX, it supports the outcalls. It will make the outcall once from your computer. It will not make it multiple times, so you will not see the problem that could occur when multiple requests are made and multiple responses are received. But for testing the code itself with outcall, it would work. It would make the outcall from your computer or whatever computer you use for running DFX. Can we use the head request to get the request size? I think we do support head requests, but I now don't remember. It's written in the documentation for sure. Yeah, I think we do support it exactly for this purpose. What's the purpose of the context? So, okay, it was not clear. In some cases, for example, we even had to use it when we implemented the exchange rate canister, which I'm going to talk about soon. We queried an API, we wanted to query an API for prices. And the API returns, and we wanted the price for a certain timestamp. And the API returns sometimes other prices because it doesn't have, for example, the time for this timestamp, so it returns the last timestamp it has, for example, and the price for it. So we needed to make sure that what we are receiving back is actually corresponding to what we wanted to receive, what we queried for, because it's not guaranteed, it depends on the API. And there is no way for us in the transform function to know what we were querying when we made the request. We don't even have the request at hand. We only have the response. So there were two alternatives. We could add the information as a header and hope the service would return this header, but that actually doesn't happen all the time. So what we did, we understood we need this context, and then what you can do is you add, for example, this timestamp that you're interested in into the context, and then in the transform function, you can access this context. And you can then decode this and find that whether this timestamp corresponds to what you received or not. Does the HTTP response have to be well-formed? I'm thinking of an API that just sent back binary data response payload. Well, it would still be an HTTP response, right? It would just be that the payload of the HTTP message would be binary. And it's fine as long as all of them are the same binary data. Or you do something in the transform function to decode this binary data to some other representation and then change it. But eventually, it doesn't matter what format the data is. Any HTTP API would respond with HTTP response with like the status code and the headers, and only in the payload it could have any like format of data. Okay, so if there are no further questions on that, let's see the Rust example. I think it's a bit bigger, but I can stay here and make it even bigger. So this is a Rust example. It's a bit simpler because it does less than the previous one. It goes to like httpsexample.com. And then we build this struct here, which is very similar to the struct we built before in Motoko. It has the URL, max response bytes. The method is selected here as get. Headers, we provide no headers here, we put them later. And body, we have none, and transform, we have none because we provide it later. Yeah, actually, we don't provide any headers. We use them only for the response. Then we create this, but less important here. Cycles, we compute the required cycles. Here we have a function for it in this example, based on this struct, the arg struct, which is actually just based on this max response bytes and the size of the whole response, the whole request, sorry. And then we call this function of the Rust SDK, which is very nice because it lets you just include a closure for the transform function, and it will have the context built into it, and you don't need to worry about this. So you call HTTP request with closure, you give this arg structure that contains the request itself, you give the cycles, and then you give this struct of headers. Yeah, you don't need these headers. It's just to create the context. So you give this context here. You create this header, which is a clone of this, and then a function, which is actually the transform function. That's the return value here. If you know Rust, it's the last line. And the function is a function that gets a response and returns a response. And what it does, it just attaches headers to the response in this case. So it just set the headers to the vector of this header because it's a single header here. So that's the transform function here. It doesn't change the response. It just attaches headers, new headers. Okay. Then we await on this call, unwrap it, and parse it. And here we check that the status is 200, but we can do whatever we want. So let me go back into this view now. Yeah, so as I said before, there are more examples in this link here, which we will have at the end as well. But this is more or less what you should do. You should create a request by specifying where you want to go. You should set the max response bytes. You could not set it if you wanted to, but then you pay for the maximal size. The maximal size is 2 megabytes. It cannot be above 2 megabytes. and then you pay for it if you don't set it. So make sure you set it. I think I don't have much time left because we talked a lot. That's good, but let's go to the exchange rate canister for a moment, because I think it's very useful. It might be very useful for some of you if you want to do something with DeFi. So the exchange rate canister is a canister, just yet another canister on the internal computer, and it's an on-chain price source developed by DFINITY, provided to the community, and it's open source. You could even deploy another copy of it if you wanted to. It is used by the IC itself to determine the conversion rate from ICP to cycles. So the cycles cost, if you know cycles, they always cost the same. They always represent the same value. They don't change with the ICP value. So the internet computer needs to constantly change or update the exchange rate between ICP and how many cycles one ICP correspond to. This is how the internal computer does it. It uses the exchange rate canister. It just calls its own, the only function it exposes is get exchange rate. You give a pair of assets and a timestamp, and you get the value for this pair for this timestamp. And that's what the internal computer itself does. The cycles minting canister on the NNS network, on the NS subnet, it calls this function periodically every 10 minutes or so with ICP to XDR exchange rate, and it gets the up-to-date exchange rate. But you can call it with any pair of assets that you want, any cryptocurrency, any fiat currency, any pair that you want for any timestamp. It could be also in the past, and the exchange rate canister will try to fetch it. It does it by sending HTTPS outcalls to multiple monetary authorities like central banks and whatever authorities in many countries that are responsible for setting the exchange rates or track them. And they have these APIs that we use to aggregate and get the right exchange rates for every date, the closing rate. And there is crypto exchanges that we communicate with APIs of the crypto exchanges to get crypto values, and then the exchange rate canister aggregates them. It caches the results. So if it gets multiple requests for exactly the same pair and time, it would return a cache response. You can see the wiki page. It has a lot of information, and you can also see the source code if you want, because it's canister. It's written in Rust. And you can use actually even use the source code to get some ideas how to do things. Just a bit about the cost. So it costs quite a bit because it makes several outcalls for each request, because it doesn't get the value from one exchange or from one central bank. It gets the value from many, and it aggregates them, and it makes sure you have enough values, and it actually gives you the information from how many it got the response, and so on. If you call it and get a cached value, you will only be charged this amount, which is very low, like 0.02 cents. If you request fiat to fiat rates, these are always cached because we always fetch the latest closing date, and then you will also pay the cached price. Now, if you start to request cryptos from crypto, we go to all the exchanges we were able to use the APIs for. So you will pay more. So fiat to crypto means we only need one rate to be fetched, and crypto to crypto means we need to fetch two rates. So you pay twice as much. And you could get an error, or you can get rate limited, because the exchange rate canister itself has rate limiting for requests, and then you're charged a small amount as well, just to prevent denial of service. The exchange rate canister runs on a 34-node subnet, so the costs are quite low compared to the value you get, because 34-node subnet means it's more secure. It makes a lot more HTTP requests for each actual request. There are 34 nodes making the same request to the remote servers. So even if you run on a 30-node subnet, the data you get is to some extent considered even more secure, because because it runs on a 34-node subnet. And with that, I will conclude and can answer more questions. Here you have links for more sample applications, the developer docs for these HTTPS Outcalls, and the wiki page. And of course, you're welcome to use the DFINITY forum to ask questions, and we answer them on a daily basis. People are using Outcalls for many different use cases. It becomes very interesting, and we see new questions every week. So it's quite exciting, and you're welcome to also join. Are there any more questions?
Not that I can see, but guys, if you have any final questions, please pop them in the chat or in the questions tab now. I see people typing, but I don't know whether they're just saying thank you. I think they're just saying thank you. So you did an amazing job answering all the questions. I hope it wasn't too many of them.
No, it was great. Great question. Thank you very much for them.
Great. Yeah, it seems like people obviously enjoyed it a lot and found the topic really interesting. So thank you so much for coming on and joining us, and hopefully I'll see you soon. Yeah. For all the participants, thank you for joining, and I'll see you guys on Tuesday, same time. You should all have calendar invites. If you don't, you can always email me or DM me on Discord, whatever you prefer, and I'd be happy to help. Like I said, tomorrow the recording will be up, so you can kind of catch up on there and review all the material. We will also be releasing the week 2 challenge tomorrow. So, but like I said, even if you haven't done week 1 challenge yet, there's still time. You can still do it. Just make sure you do it at some point, because then you'll be in the running for some really cool prizes. So yeah, that's it for me. Thank you, Yotam, and thank you, everyone. Have a nice rest of your day. Bye, guys.
Thank you. Bye.